Hi, kids. It's Mrs. Geiger. So I'm going to record for you the beginning of this is going to be Unit 9, which is called Acids, Bases, and Salts. And this is my most favorite unit of the entire year. And that's because acids and bases often change colors when they come in contact with other substances. So just my favorite because it's the most colorful. The other thing that you should know about this unit is that it focuses on my favorite molecule. That's right, you know it, it's water. So I'm just going to go ahead and draw a water molecule here. I'm going to make my oxygen. There we go. Make my oxygen blue. And I'm going to go ahead and make my hydrogens red. And remember, we're going to make this a bent molecule. Let's make that red. All right, and then I'm going to go ahead and I need 2 of these, obviously. So remember, water is bent. So there's my H2O molecule. So go ahead and in your notes, you're going to write down acids, bases, and salts, and you're going to draw yourself a water molecule, just like I did there. All right, so we're gonna go through a few definitions for acids and bases, as well as what you should know, which is the pH scale. All right, so definitions. Originally, acids and bases were defined by how they tasted, but as we know, you can't go around licking things. So, the word acid comes from ácido, and all my Spanish speaking friends out there know that ácido means sour. So acids are things that tasted sour. All right. And in your head right now, think about what types of substances you know that are acidic, specifically foods. All right. So bases are opposite of acids. Acids and bases are opposites of each other. So bases actually taste what's called bitter. Now, bitter is probably the taste that you have been avoiding. Things that are bitter are like dark green, leafy things like spinach and broccoli are bitter. Coffee is bitter. So sour and bitter are not the same thing, but also, interestingly enough, bases feel slippery. And lots of cleaning products utilize bases in order to do their cleaning. So ammonia, the main ingredient in Windex, is actually a base. So that's one of the ways that you can remember that bases feel slippery. They're used as cleaning products for this reason, and they taste bitter. All right, so we're going to go through a few definitions. These definitions, they don't contradict each other, but we're going to go in chronological order. So the first scientist we're going to learn about is Arrhenius. Arrhenius, you say it like he was a genius. Arrhenius came up with a definition for acids and bases that had to do with the chemical composition. Now, something that you should know is that I put a water molecule up here for a very important reason. And that reason is that it turns out that what makes substances acidic and what makes substances basic. And another word you should know for bases are alkaline. So you should put this here that base. So I'm going to just put acidic is the adjective for something that is an acid. If you are a base, you're basic. Oh, but I would never call you basic. Or alkaline. Now, we've heard this word alkaline before when we did the periodic table unit. You should remember that Group 1 and Group 2 make alkaline substances. That's why they're called the alkali metals and the alkali earth metals, respectively. So that's going to come up again, and that has to do with how those metals interact with water. So it turns out that water is constantly associating and dissociating when it is in a container or anything. So when you have a sample of water, some amount of those water molecules are constantly dissociating and associating. Now, do you remember what dissociate means? Right, so dissociate means that they're going to break apart. So when this happens, the hydrogens don't go together, but instead, just one of the bonds is broken. So when, oopsie, let me go back. I didn't mean to change the shape of that, but I did want to dissociate it. So when water dissociates, it's going to break up into a hydrogen and a hydroxide. So it's going to associate and it's going to dissociate. And when it dissociates, that hydrogen is going to be breaking off. I'm actually going to open up a new screen right here so that we can draw the Lewis electron dot diagram for water. So when this happens, hydrogen does not take its own electron. Instead, it leaves its electron behind, and I gotta fix that font size. It was just too small. So it leaves that electron behind. The reason it leaves the electron behind is because oxygen is so much more electronegative. So it is holding on to this electron, this hydrogen electron, closer than the hydrogen can. Remember, water is polar because of this. So when the water molecule dissociates, the hydrogen, oh, it doesn't know that that's one thing. The hydrogen leaves its electron behind. So it's going to dissociate and it's going to leave its electron behind. I'm just going to move this whole thing over to the middle. All right, so here's my water molecule, and here is my ionization or my dissociation. So when this happens and it leaves its electron behind, it becomes charged. Now, water is neutral, but when it ionizes, or when the hydrogen dissociates from the water and it leaves its electron behind, think about this. Hydrogen was an atom and it had an electron. If it loses an electron, what will the charge on that hydrogen become? That's right, it's going to end up with a +1 charge. All right, so we end up with hydrogen ions, and then this is also an ion. And this is a polyatomic ion that you should recognize. This polyatomic ion ends up with this extra electron, the electron that the hydrogen left behind. So this ends up with a -1 charge. So when a water molecule dissociates, it's going to break apart into a hydrogen ion and a hydroxide ion. So we can write this dissociation like this. Water is breaking apart into a hydrogen ion and a hydroxide ion. And this is always, always happening. Whenever you have a sample of water, some amount of the water molecules have broken apart, and then they come back together, and other ones break apart and come back together, and this is constantly happening. So there's actually a ratio for this, and we know what this ratio is. And we know that ion here, we know, is just a hydrogen ion. And this here we know is called a hydroxide ion. And it turns out that if one water molecule breaks apart, it's going to create one hydrogen ion and one hydroxide ion. So for every time that happens, for every time you create one hydrogen ion and one hydroxide ion, how many water molecules did not change? What is the ratio? It turns out that for every one hydrogen ion that's created, you have 10 to the 14th power water molecules that did not dissociate. So you have 1 times 10 to the 14th water molecules that are associated, which just means that they're regularly bonded. And you have one hydrogen ion and one hydroxide ion in solution. So that's the ratio. For every 1 times 10 to the 14th water molecules, one of them has dissociated. And that's a constant that we know and that we've measured. More to come on this because this has to do with pH and the pH scale. So let's go back to our original slide and go back to talking about Arrhenius. So once we figured this out, Arrhenius defined acids as a substance that increases the hydrogen ion concentration in an aqueous solution. All right. Now Arrhenius looked at the other side of water molecules and said that a base is just the opposite of that. It's the other piece of the water molecule. So a base is a substance that increases the hydroxide ion concentration in an aqueous solution. All right, so let's do some examples. The most common example for an acid is hydrochloric acid. Hydrochloric acid is stomach acid, so you have it in you right now, and it also, because chloride ions are so common, when water comes in contact with chlorine or a chloride ion, often makes hydrochloric acid. So when this hydrochloric acid dissociates, when it breaks apart into its ions, it's going to make a hydrogen ion and a chloride ion. All right, so anytime a substance increases the amount of hydrogen ions that it has in a solution, then it's going to be an acid. The chloride ion here is called the conjugate, just the other side of that molecule or substance. So our example for our hydroxide or our basic solution here is going to be sodium hydroxide. All right, and it's also going to be aqueous here. And when sodium hydroxide dissociates, it's going to form a sodium ion and a hydroxide ion. So again, anytime a substance dissociates, and when it dissociates, that dissociation increases the amount of hydroxide ions in solution, then it is considered to be a base.